And
Yeah, this is the full screen. Yeah, the slideshow mode.
and if I want to move to the Excel sheet,
Yes, you press, yeah.
yeah, the F3. And
Yes.
again, I'll have to press F3 if I want to go
Yes.
back to this.
Yes.
Right,
Yeah,
so I stop
it
sharing.
works.
Thank you.
Okay, we still have like 1 minute actually.
Yes, yes, sure. But
Yeah.
how long should we do the session? I mean, I am ready for to do up to 2.5 hours with a short 15-minute break if people want, or whichever
Yes,
way is
yes.
up to you. But I will tailor the session accordingly. Like I have lots of activities, but I'll do some depending on the time that we have. So
Yeah, sure. We can have like up to 2.5 hours with 15-minute breaks. And yes, more on the experiencing the spreadsheet that will take some times for them
yes,
to
yes,
input the formula. So I think
correct, correct.
the participant will not really feel it like long, because when they're doing something, it would be
Yes,
it
yes,
would be like so fast. So
right,
yeah, maybe 2.5 hours will be so quick if we do something.
correct.
Yeah. So is it okay like 5 minutes
Yeah, yeah, sure,
again
sure.
to
Please,
wait
please.
for
Yes,
the participants?
absolutely.
Okay, thank
Yeah,
you.
sure. I'm here. I'll just stop my video
Yes,
for a minute.
yes, thank you. Bapak Ibu, Assalamualaikum warahmatullahi wabarakatuh. Selamat bergabung di sesi 3. Mohon untuk merename namanya, yang guest menjadi namanya Bapak Ibu semuanya ya. So, Dr. Jonaki.
Yes, yes.
Okay, so it's 5 minutes already in some part of Indonesia. In this part and the middle part, they having like praying, so they will join right after they finish the praying. Meanwhile, we can start. And then before that, I would like to introduce you to our participants in Bahasa Indonesia. Is that okay?
Yes, thank you. Thank you very much. Yeah.
Okay, now I would like to introduce our today's facilitators. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore, selamat malam Bapak Ibu semuanya yang hadir dalam kesempatan hari ini di webinar sesi 3 terkait computational thinking bagi guru matematika yang pada kali ini akan mengeksplorasi tentang penggunaan spreadsheet. Kali ini kita akan dibersamai oleh narasumber kita yaitu Dr. Jonaki Gos. Beliau adalah Associate Professor di Departemen Pendidikan Dasar di Universitas Delhi, di New Delhi, di Lady Shriram College. Kemudian beliau mengajar mata kuliah pendidikan matematika. Penelitian yang diminati beliau adalah penggunaan teknologi untuk pembelajaran matematika, terus kemudian pelatihan guru atau peningkatan keprofesionalan guru matematika, dan juga mempopulerkan matematika. Jadi matematika akan dibuat populer oleh beliau. Kemudian beliau juga sudah mempublikasikan jurnal-jurnal internasional dan juga proceeding di conference. Ya, jika Bapak Ibu menghadiri conference di ETCM mungkin sudah mengenal beliau, seperti waktu itu saya mengenal beliau di conference tersebut. Kemudian Dr. Jonaki Gos juga memberikan speech atau sesi di beberapa konferensi internasional termasuk workshop, dan kali ini juga akan memberikan semacam workshop kepada Bapak Ibu semuanya. Beliau juga membuat sebuah fondasi atau semacam LSM, Ramanujan Foundation for Initiative in Mathematics Education, yang intinya juga tentang pelatihan keprofesionalan guru matematika. Workshop yang dia berikan berfokus pada praktik-praktik inovasi dan juga kegiatan hands-on di pembelajaran matematika, penggunaan teknologi, dan juga memperdalam pemahaman konten matematika untuk guru-guru, dan juga dia juga membantu beberapa lab school di beberapa sekolah. Okay, that's it. Without further ado, Dr. Jonaki, the floor is yours.
Thank you. Thank you, Wahid, very much for this kind introduction. Before I continue, is everybody
mendengar ini?
Yes,
will
yes,
everybody
Doctor.
become comfortable in English?
Yes,
Or-
in English.
Right. So if you feel I need to stop at some time and you want to explain in your language, that's also fine.
I will do that. If it is unclear
Yes,
or too fast, then yeah. Okay.
Do let me know. Okay. So thank you, and this is a warm welcome to the participants. I'm just going to share my screen now. Yeah, so I just. Is it visible?
Yes.
Yes. So welcome to all the teachers from Indonesia. I am Jonaki Ghosh from India. So namaste. The title of, so when Wahid asked me to do this workshop, and he mentioned that the topic is integrating mathematical as well as computational thinking through spreadsheets, I became very interested because this is also an area of interest for me. So I hope you will find this hands-on workshop interesting. So of course, I would like to thank Wahid Yudianto for this invitation and for the organization MN for conducting this workshop on computational thinking in mathematics education. So let me just share with you what I will do through this session. I would teachers be having access to Excel right now? So I just wanted to know if teachers will be able to they have access to Microsoft Excel right now. I assume that some teachers would be having that. Am I right? Am I audible?
Yes, they have Microsoft.
Okay, sure. Thank you. I'll start with a very brief overview about computational thinking, highlighting its connection with mathematical thinking. But the main thrust of this the session will be that we'll look at some exploration of open-ended problems, which have been tried out with middle school as well as secondary school students, in which they engaged with computational and mathematical thinking using spreadsheets, and it was an inquiry-based approach. And of course, I'll end with some suggestions, but that's at the end, suggestions and implications for the curriculum. So when we talk about computational thinking, the first name that actually comes to mind is Samuel Papert. Just a second, please. Yeah. Who talked about children using computers as instruments for learning. And he was one of the main people who was responsible for using the term computational thinking. And his very well-known and famous book, Mindstorms, he talks about turtle geometry and logo programming. And through this, he introduced a computational style of learning geometry. So this is a book worthwhile for teachers to look at. And of course, everyone whoever is interested in computational thinking must have heard the name of Jeanette M. Wing, who in 2006, in her very short paper in the ACM Communications, this was a snapshot of the paper, she popularized the term computational thinking. And she said that computational thinking is a fundamental skill for everyone, not just computer scientists. So to reading, writing, and arithmetic, the 3 R's, we should add computational thinking to the analytical ability of children. And the basic framework of computational thinking says that, it consists of these 4 aspects. So the key ideas are decomposition, decomposing a problem into simpler problems, smaller steps, pattern recognition, abstraction, and then algorithmic design. So this is what normally the framework, very popular framework to explain computational thinking. And the group by David Winthrop, a group which has been really engaging in computational thinking, lists out these are the skills. They talk about these skills which we need to develop, which are called computational thinking skills. And that is the ability to deal with open-ended problems. So this is something that I would like to focus on more in this workshop. How we can make children do explorations and work with open-ended problems. Persistence and confidence in dealing with complex ideas. So even through these explorations, children can deal with very sophisticated ideas. Representing ideas in computationally meaningful ways. Breaking down problems into simpler, we already mentioned that is decomposition. Creating abstractions. So even David Winthrop's computational thinking skills are related to this diagram that you can see here. Moving on, you know about the international student program for the international student assessment, the PISA 2021. The mathematics framework of the PISA 2021 acknowledges the long-term, they use this sentence in their document, the long-term trajectory of mathematical literacy should also encompass the synergistic and reciprocal relationship between mathematical and computational thinking. So mathematics, we as mathematics teachers, I think the onus is more on us to engage in our learners in computational thinking. Although computational thinking is something that can be applicable to any subject and can be integrated in any subject domain, but mathematics is perhaps a more natural subject where computational thinking can be integrated. So many people ask, what is the difference between mathematical thinking and computational thinking? Are they same? Are they different? So I would say that MT, mathematical thinking and computational thinking practices are distinct and yet mutually supportive. So there are some similarities and some subtle differences. But the challenge is that what kind of tasks as teachers, the challenge for teachers is what kind of tasks do we need to identify which allow students to develop and employ both CT practices and also engage in mathematical thinking. Technology certainly is a tool. So today we are going to look at spreadsheets, but any dynamic software or computer algebra system, so all these together play an important role in mediating computational mathematical thinking. And I like this to use this diagram, which says that as you can see, there's an overlap between computational and mathematical thinking. So problem solving is common to both. Dealing with recursive ideas, modeling, simulation, all these are common to both mathematical and computational thinking. But probably computational thinking focuses more on algorithmic thinking and coding, little bit of coding. And mathematical thinking is more about justifying solutions, reasoning, and proof, developing proof. But the part which is common to both, I think this is what we can cash in on and we should focus on when we develop tasks which enable learners or students to engage in both CT and MT. So why spreadsheets? I mean, why should we use spreadsheets? Very often teachers tell me that there is GeoGebra and there is Desmos and there's such nice open source tools. Why should we use a spreadsheet? I mean, spreadsheet looks like a sheet with just cells and rows and columns, and that's not very interesting to children, or students. But I disagree. I feel electronic spreadsheets, if used in the right manner, can really serve as a nexus between the big ideas in mathematics. So if you are familiar with, there are 21 big ideas in mathematics, like number patterns, equivalence. These are ideas or strands that have been identified in mathematics curricula across the world. So electronic spreadsheets can really be a nexus between the big ideas of mathematics and computational thinking. And mathematics teachers need to be able to convey these big ideas to their students. So we need to engage students in meaningful problem solving and explorations. Spreadsheets are very useful because they are very suitable for designing inquiry-based tasks. And best part about spreadsheets is you can do extensive coding also, but children do not need to have extensive knowledge of coding to be able to use spreadsheets. So simple commands or simple conditional statements are enough to engage with fairly involved and difficult problems. So this is what I would like to focus on in this today's session. Before I proceed, I just would like to know right now how many participants are there. About 69. So how many, is it possible, Wahid, to make this interactive? Like, I would just like to get an idea of how many people might be teaching at middle school level or at secondary level. Is it possible to know that? Or
It's possible.
Okay. So actually, if there is a rough estimate that there are more middle school teachers or are there more secondary school teachers?
Oke, Bapak Ibu boleh tuliskan di chat box mengajar lebih ke SMP atau SMA?
I think if you are a middle school teacher, you just say M, and
Yes.
if you're senior school. Okay, so what does SMP mean? See,
SMP is junior, SMA is senior high school. Yeah.
okay, second. So there seem to be a mixed.
Yeah.
Yeah, great,
But
great.
so far, yeah, let's see.
Right, right. Thank you very much. But is everybody able to understand what I'm saying? I mean, is it all right?
Bapak Ibu dapat dipahami sesinya? Jempol jika masih bisa mengikuti.
Okay, great. Thank you very much. Thank you for your, yeah, great, wonderful. Thank you so much. Okay, so the first thing that I would like to discuss is, exploring number patterns is something very natural that we would like to do using a spreadsheet. And even young children, like I have done these tasks, with fractal-based tasks with students of grade 8, 7, little bit of 7, grade 7, grade 8, grade 9. And it can go across to grade 12. Because fractals are usually not a part of the curriculum. So in India, fractals are not taught in school, but they can be an excellent way of introducing patterns, number sequences. So this is the first thing that I would like to share. So geometrical fractals, like everyone, those who know about fractals, are familiar with fractals, would know about the Sierpinski triangle, Sierpinski carpet, chord snowflake, and all. Pythagorean tree. And children also like to, you can give them tasks where they generate or create their own fractals also. While exploring fractals, we use the idea of multiple representations. That means we can look at fractals pictorially, numerically on a spreadsheet, graphically, and also symbolically. So all these 4 modes of representation, which we also often refer to as the rule of 4, can be used. And technology can help us a lot, like for creating, for using pictorial, creating pictures of fractals, GeoGebra can be useful. I think you may have to mute some. GeoGebra, Mathicon, Mathematica, these are very useful for creating pictures or pictorial representations of different stages of fractals.
Wait,
yeah.
Yes, I'm mute already.
Okay.
Okay, please.
Yeah. And for numerical and graphical representations, spreadsheets can be very useful. And what are the mathematical concepts? Like these are the concepts which are dealt with in middle school, like area, perimeter, and little higher classes, geometric sequences. And then you can go beyond the curriculum, like identifying self-similarity in the fractals and computing fractal dimension and so on. So there is a whole range of activities and concepts that you can deal with. And children can engage in the mathematics while learning mathematics. One of the most important things children have to do is generalize patterns, generalization of patterns. So recursive, explicit, and all, so visualization is possible. We of course see a lot of fractals in nature. So if you look at certain kind of leaves, which have a central branch, and along those there are smaller leaves. And if you look at a smaller leaf, it's a kind of a replica of the whole leaf. It's a copy of the whole leaf. And within that, there are smaller leaves. Or if you look at a cauliflower and you take a small portion of the cauliflower and you magnify it, it resembles the bigger cauliflower. If you look at you cut the cauliflower into half and you look at the cross section, that also has a fractal structure similar to the branching of trees, where there is a central branch and then splits into smaller branches and those in turn. So if you look at any small portion, it is somewhat similar to the whole. So fractals exhibit similar patterns in progressively smaller scales, and they are very much around in nature. And of course, it was Benoit Mandelbrot who had looked extensively studied fractals. So fractal geometry should be a part of the curriculum, but even if it is not a part of the main curriculum, we can do some activities and explorations using fractals. So the simplest one, of course, is the Sierpinski triangle. I just want to know just from the audience that are you familiar with the Sierpinski triangle? Just Y for yes will do, if you are familiar.
Ditulis pernah mendengar Sierpinski triangle, segitiga Sierpinski? Yes or no?
No.
Oh, okay. Not yet.
Not yet.
Okay,
Most
great.
of them may be not familiar with this.
Sure. That's nice because then
Because it is not in the school curriculum yet.
Yeah, exactly. It's not in the curriculum in India as well. Yes, that's true. Okay, so let me tell you, this is a very beautiful thing. So what we do, we have an equilateral triangle. Let's say this is this black, it's a cutout, a cardboard piece, let's say. And what we are going to do to this is, let me take my pen. I can take the midpoints of these three sides of this equilateral triangle, join them, right? I have four smaller equilateral triangles. And since it's a cardboard piece, I can just cut this out. Just cut it out and remove it. Okay?
Okay, may I re-explain a little
Yes,
bit to Indonesian teachers?
Yes, please.
Jadi untuk segitiga Sierpinski fraktal ini, pertama ada segitiga utuh, Bapak Ibu, di titik-titik tengah di sisi-sisinya itu dibuat segitiga lagi. Nah, yang segitiga tengah itu dibuang, jadi bolong. Nah, itu akan diulang terus-menerus begitu. Oke, silakan. Please continue.
Yes. Okay, so this is what we do. So, sorry. So I'll just, yeah. So this was what we started with this equilateral triangle piece, and we joined the midpoints and we made four small, and we removed the center triangle. So when you remove the center piece, this is a gap, it's a hole, right?
Yes.
So how many equilateral, this is a single equilateral triangle, but how many small equilateral triangles can we see now? If you could write in the chat.
Silakan, ada berapa banyak segitiga sama sisi kecilnya?
Three.
Three, yes. Four because it is four, but we remove and throw it away, the middle one, right? It's a hole now. The white portion is no longer there.
Yang putih itu berlubang ya Bapak Ibu ya.
Right. Now we repeat the same process on all the three smaller triangles. So what we will do here, again, we will join the midpoints of these three and remove this. Same thing we'll do here. And the same thing we'll do here. We remove these portions. So next stage, so a fractal is developed in stages. Next stage, how many black triangles will you have?
9.
9.
Excellent, excellent. So I'm just going back so that I can.
9.
Yes, absolutely correct. Next stage will look like this, right? Now there are 9 small black triangles. Again, we repeat. So this is recursion. So you keep repeating the same thing. Now the same thing will be repeated on all the small 9 triangles. So next stage, how many black triangles will we have?
Uh,
27.
27.
27.
Fantastic, fantastic. Yes, indeed, it will be 27 because each triangle will lead to 3 smaller black triangles, right? So that this is what it will look like. And if one can go on, but it becomes very complicated after some time, right?
Ini jawab. 81.
Yes, absolutely. So instead, this initial stage is called stage 0 because that's the starting stage. We call it stage 0 in a fractal construction. Then stage 1 has 3 triangles, black triangles. Stage 2 has 9 black triangles. Stage 3 has 27. And somebody just told me that stage 4 should be having 81 triangles. Fantastic. So now as a teacher, suppose you were to give this task to show this picture to your students, what questions would you like to ask them? One is, of course, in every stage, how many black triangles are there, right? Is there any other question that you would like to ask them, to your students, related to this figure? Yeah.
Ada pertanyaan untuk diberikan ke siswa Bapak Ibu jika menyajikan ini? Okay, can you see the patterns?
Oh yeah, yes, okay. What pattern can you get? That's, yes, but can you make it more specific, like one is number of black triangles. Would you like to ask them something else, like related to area maybe?
Adakah yang ingin menanyakan luasnya? Terkait luas? Kalau menanyakan luasnya gimana Bapak Ibu?
Okay, so let me say one question which I asked you, when you can ask your students, how many shaded or black triangles will there be at the next few stages? So they can see stage 0, 1, 2, 3. At stage 4, 5, 6, how many black triangles can you see? Okay. Now, is there a pattern in the number of black triangles? And what pattern is that? Can anyone explain? Or you can just share your ideas and thoughts.
Silakan Bapak Ibu, gimana polanya atau rumusnya untuk menentukan segitiga yang hitam? Boleh ngomong langsung, boleh di chat. Silakan yang ingin ngomong langsung boleh.
3 pangkat n bukan sih?
3 to the power of n.
N pangkat 3.
N to the
Yes.
power of 3. Which one is correct? 3 to the power of n or n to the power of 3? There are two
Yes.
Answers, Dr. Janaki.
Yes. 3 raised to the power n. Indeed, it is so. So what you can ask this question, can you find a rule for the number of shaded triangles at the nth stage? So you want them to generalize, right? So one is stage 4, how many? 81. Stage 5, how many? So each time for every stage, what are we doing? We are multiplying by 3. So here there is one black triangle in stage 0. In stage 1, there are 3. In stage 2, there are 9, which can be written as 3 square. And at stage 3, there are 27, which can be written as 3 cube. And so on. So can you find the rule for the number of shaded triangles at the nth stage? So we want them to write for any given stage, right? So we can see that the stage number and the exponent of 3 is coinciding. So we can say that at the nth stage, maybe you can get the children to observe that it will be 3 raised to the power n. But it is also interesting to ask the children that this is an equilateral triangle. Am I right?
Yes.
So what is the area? Suppose I say that this area, this whole area is say 1 square unit. So how much is the black area now here?
1/3.
1/4.
1/4.
The total area, the total black area.
Yang hitamnya
3/4.
3/4.
Yes, yes, absolutely. Because
Rapat.
you are dividing the original triangle into 4 equal parts and you're removing one part. So 3 out of 4. So this is 1/4, this is 1/4, this is 1/4, right? So 3 out of 4. The area will be 3 out of 4. The area is 3 out of 4 in this stage. But at this stage, what is happening? What is the area now? At stage 2.
Berapa luasnya di stage 2 Bapak Ibu?
9/16.
9/16.
9/16, yes. How did you guess that?
Bagaimana caranya?
Yang 9-nya itu yang segitiga hitam, dan 16-nya itu jumlah segitiga kecilnya itu yang putih dan yang hitam.
How did you get 9? Berapa bisa dapat 9-nya dari?
9 dari segitiga yang hitam. Kemudian yang 16-nya itu dari jumlah segitiga yang hitam, dan yang putihnya itu karena ukurannya sama.
3/4 pangkat N.
I think they counted the number of triangles. Is that it?
Yes, I think.
Or you imagine that the triangle, the big triangle is divided into 16 smaller parts and 9 are shaded perhaps. But indeed it is 9/16, which is 3/4 whole square. Why? Because every time you are removing, so the black portion is, so this black portion is 3/4 of this portion, and this black portion is 3/4 of this, because you're dividing each of these triangles into 4 smaller parts and removing one part.
Yeah.
So at this stage, this will be 3/4 of this, and at the next stage, it will be 3/4 of this, which will be, of course, 27/64, or 3/4 cube. The area, the black area. So one interesting question that you can ask is, one of course is, how many black triangles are there at the nth stage or at any given stage? And what is the shaded area, the black area at the nth stage, if the area at stage 0 is 1 square unit? So you can just fix the area at stage 0. If it is 1 square unit, then this is 3/4, this is 3/4 square, this is 3/4 cube, and so on. And this is an infinite process. So you can bring in the idea of some process going to infinity, going on and on and on and on forever. So what happens as n is what? N denotes the stage number. So this is stage 0, this is stage 1, this is stage 2, and this is stage 3, and so on. So what happens as the number of stages becomes very large? So what happens to this fractal, this Sierpinski triangle fractal? What happens to the black portion area? So can you tell what is happening to the black area? Is it increasing? It is decreasing? What is happening?
Become smaller.
Yes, very good. So it is becoming smaller, lesser and lesser, right? Now, one child asked me, one middle school children are very, very smart, intelligent. They asked me that, why are we only looking at the black triangles? Why can't we look at the white portions? So some other child said, oh, that's cut away and thrown away. But one child said, but I want to calculate the area of the white portion which is being cut out. Right? So that's also an interesting problem to explore, because see, the white portions are increasing, isn't it? Here we have a single white hole. This is a hole actually. And that is why this Sierpinski triangle is also called the Sierpinski sieve. It's also like a sieve because holes are coming up, right? And it's very difficult. I mean, there are computer programs which generate these fractals, but I can show you some interesting work that can be done with artwork, which can be done with these fractals. So what happens is n tends to infinity, or n increases, the black area or the colored area goes on decreasing, becomes smaller and smaller, right? And the white holes, the area becomes bigger and bigger. Okay. Then the last question is to do with self-similarity, which I will tell you a little later. So what should we do? When you ask the question, ask the children to make a table like this, where you write the stage number 0, 1, 2, 3, 4, and then finally what is there at the nth stage. And you told me that for number of black triangles, at stage 0, it is 1 triangle. At stage 1, it is 3. So I wrote 3. At stage 2, it is 3 square, which is 9. At stage 3, it is 27, and so on. So at stage n, it is 3 raised to the power n. That is the number of black triangles. So putting it in the form of a table is useful for children. And what is the shaded area? I said let the shaded area be 1 square unit, this black area. So here it is 3 upon 4. Here it is 9 upon 16, which is 3 upon 4 square, and so on. And again, you see the exponent, the power is the same as the stage number. So at the nth stage, the area of is 3 upon 4 raised to the power n. But as n tends to infinity, as n becomes very large, what happens? So as n approaches infinity, becomes very large, what happens to 3 raised to the power n?
Apa yang terjadi Bapak Ibu jika n mendekati tak hingga? Belajar kalkulus ini.
Jadi
So middle
Zero?
school, middle school children will not be able to use the word limit or infinity. But you can ask them questions like what happens as n becomes very large? At higher stages, what will happen? So what happens to the number of black triangles? 3 raised to the power n also becomes very, very large.
Yes.
We say this approaches infinity. But what happens to the area? You can see area is decreasing. So
Areanya bagaimana? Mengecil atau membesar Bapak Ibu? Smaller or larger?
smaller.
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 So 3 upon 4 raised to the power n will approach 0. Now, this may not be very convincing to children. So what do? We can take them. So now I want to try and go to the spreadsheet. Yeah. Can you see spreadsheet?
Bisa melihat spreadsheet atau Excel Bapak Ibu?
Yes.
All right. So let me make it 150%. So let's have stage number of the Sierpinski triangle, and we have a number of triangles, black triangles, colored triangles. These are just comments, just for your understanding. And shaded means black. In my fractal, it is black. You can use any color. Okay. So stage number, we start with 0. Now suppose I want to see in my picture, when I drew the Sierpinski triangle, I can see only up to stage 3 or 4, maybe. But I want to know what is happening at stage, let's say stage 10, or even stage 20. What's happening to the Sierpinski triangle? So I can do a numerical exploration by writing the stage numbers from 0 to, let's say, 20. So what do? I enter this formula here in this cell. So I enter 0 here and I put equal to, click on 0, the previous cell, A2, and plus 1. If you are trying it out on your spreadsheet, you can try it out.
Silakan Bapak Ibu sambil mencoba supaya tahu bahwa rumus ini biasanya kan ditarik ke bawah langsung otomatis kalau ini menggunakan rumus.
So if you would like me to wait.
Spreadsheet-nya. Yes, okay.
Okay. So if I enter 0 as the stage 0, then next cell I type equal to previous cell, that is A2 plus 1. I don't need to type A2. I just need to click on the previous cell and type plus 1 and press enter. Now, the formula is in this cell. So I can go to the corner of the cell where the cursor becomes a plus symbol, and I can drag
Dari ke bawah.
I need up to stage 20, right? Stage 20. One more. And I'll just center align these. Right? This is your
Yes.
comment, so I'll just give it a different color and bold. Okay, So I have stage number 0, 1, 2, 3 up to 20. So what, do you remember the formula for the number of triangles at stage n? What was the formula? We just did it. So you told me the formula.
3 pangkat N.
3 raised to the power n. Right? Excellent. So I will enter here equal to 3 raised to the power is above number 6 on your keypad, raised to the power. I have to type in the formula equal to 3 raised to the power n, but n is here, n is in column A. So I just click on this, A2. So the formula was 3 raised to the power n, but instead of n, I'm going to click on the cell here. Is it okay?
Yes.
So when I press enter, I will get, why do I get 1? Because it is 3 raised to the power 0. Now I just need to come to the corner of the cell. Whenever there's a formula, I just double click. All I did was I went to the corner of the cell and double click because I already have a column A with numbers. So now if I have a formula here and I don't need to drag, I can drag, but I don't need to drag. I can just double click. Now, what will students say? What will your students say if you show them this? If they do this, what will they say? What's happening to the number of triangles?
Apa yang akan dikatakan siswa Bapak Ibu saat melihat sel kedua?
What do you think children will say? Yeah. They'll say number of triangles is getting?
Number of the angle increasing.
Larger, increasing.
Yes, absolutely. Getting bigger and bigger and very fast, like it's growing really fast, right? And so if you want, you can just click on this column, just click on B. B is the column. So you click on the column B and you go to charts. If you have charts with you on your Excel sheet, and in charts, you can select a line chart. Whatever you have, I don't know what version of Excel you might have, but you will have something to do with charts and with a line graph. And you can see that I can remove this index. So number of triangles is growing fast. It suddenly grows, right?
Exponentially.
Yeah. And the reason is that this is a geometric sequence actually. So it's growing very fast. Now let's come to the area, the black area. What was the formula for the black area? Do you remember?
Masih ingat rumusnya Bapak Ibu?
3/4 pangkat N.
3/4 to the power of n.
Yes. So I type equal to 3/4 raised to the power n. Again, instead of n, I will click on this because the n value, n represents the stage number of the fractal. And the stage number is in column A. So I just click here. So here I had to type equal to 3 raised to the power stage number. And here I will type 3/4 raised to the power stage number. So when I press enter, again, it is 1 here, but if I double click here, so what is happening to the area? What will you say?
Smaller.
Smaller.
Yes. And we can click on this column, again, do a line graph and see that
mendekati 0.
Yes, the area is getting, the shaded area is getting, it's starting at 1, but it is getting less and less and going to 0. But the number of triangles is growing very fast. So in the construction of the Sierpinski triangle, two opposite things are happening. One attribute, that is number of triangles, is growing very fast, and the other attribute, that is area, is going to 0. So you can explain these ideas. These are ideas. Now, middle school children, especially in grade 7 and 8, will now begin to associate numbers with a graphical representation. And, that could be something very useful to do with children, because they have seen the picture of the fractal, that's pictorially. Now they are seeing it numerically on the spreadsheet, and they're also seeing it graphically. And they also know that the formulas are 3 raised to the power n and 3/4. So that is symbolically. So multiple representations. Which are the 4 representations? Pictorial, graphical, this is graphical, this is numerical, and symbolic. So these 4 representations together help to build the concept. So I hope you like the idea of this Sierpinski triangle. I will go back to my this thing. You can try it out. So I will share all the steps that you have to do to get your spreadsheet work done. So don't worry about that. The other interesting rule that you can ask children to observe is, if we say that the number of black triangles is T of n, T bracket n, then the recursive rule says that at every stage, the number of black triangles is 3 times the previous stage. So 27 is 3 times of 9, 81 is 3 times of 27. So at nth stage, it is 3 times the previous stage, which is the n-1 stage. Similarly, if you look at shaded area, at any stage, the area is 3/4 times the previous stage. So in this case, in the case of number of black triangles, we have a multiplying factor of 3. And here we have a multiplying factor of 3/4. And all these are, both these sequences of numbers are geometric sequences, right? Do you teach geometric sequences in school? If not in middle school, but definitely in grade 10 or 11, you would be dealing with geometric sequences, arithmetic sequences and geometric sequences. But in fractals, you will always get geometric sequences, whatever attribute of the fractal you observe. Now, there are many interesting things related to this. Sorry. So this we already saw. This is a snapshot of only up to stage 10. So children can see that the number of shaded triangles is growing fast. So they can associate these numbers with this graph of growing, and the shaded area is getting lesser and lesser. So growing fast and getting lesser and lesser, 2 opposite things are happening. Now, okay, so this is one stage of the Sierpinski triangle. So can you tell me which stage this is? I think by now you can guess.
Berapa Bapak Ibu? 4 atau berapa?
Stage 0 has 1 single triangle. Stage 2 has 3. Stage 0 has 1 single triangle. Stage 1 has 2 triangles. Stage 1 has 3 triangles. Stage 2 has 9.
Or stage 4.
This is stage, how many triangles? Black triangles?
T1.
No, here we have 27. So 27 is?
Stage 3.
Right?
Stage 3.
Excellent. Yes, this is stage 3. Now, look at this circle. What is inside this circle? What stage is this? Only this inside the circle?
Step 2.
Stage 2, because there are 9 triangles here. So, how many copies of stage 2 can you see inside stage 3? So this
Berapa
this
kali
Two.
stage ketiga?
3.
Yes, because this is stage 3. You have a stage 2 here, you have a stage 2 here, and you have a stage 2 here. So Stage 3 has 3 copies of stage 2. Now let's enlarge stage 2. This is, suppose we are using a lens, a magnifying lens. This is stage 2. And what is this stage? 3 triangles.
Stage 1.
Stage 1. So how many copies of stage 1 do you see in stage 2?
3 copies.
3 copies. Yes, absolutely. So this goes on, and this is stage 1, and this is stage 0. So we have 3 copies of stage 0. So at every stage, you can see copies of previous stages. Not only that, again, this is stage 3, right? This is stage 3, same stage. Stage 3. And now look at this small circle. What is inside this small circle? Which stage?
Stage 1.
Stage 1, very good. How many copies of stage 1 do you see in stage 3?
9 copies.
9 copies. Excellent. So, and similarly, in general, we can generalize the statement. The stage n has 3 copies of stage n minus 1, 9 copies of stage n minus 2, and so on. So from the particular case, you can go to the general. And these ideas are important because these are an important part of mathematical thinking. And what we are understanding here is recursion, the recursive way of looking. Fractal constructions happen recursively. So fractals are a good way of introducing the idea of recursion to young children. Moving on from the, did you like the Sierpinski triangle idea?
Suka tidak Bapak Ibu dengan idenya segitiga Sierpinski fraktalnya?
You can say no, it's absolutely fine. Do you think? So you can try to do it with maybe grade 8 students, grade 9, right? If you are teaching them. Younger children also enjoy. But
Yes, so enjoy.
you enjoyed? Okay, great. I'm so happy. Okay.
Maybe
Now,
interesting to apply for the student.
yes, yes. Generally, children enjoy it very much. So now I want to show you something else, which is I won't be able to do the entire thing in detail, but it's very interesting. And you can do it with slightly older children. Same idea. It's again a fractal. So what we do is we take a straight line, okay? And we divide the straight line into 3 equal parts. So let's say this is a straight line. I divide it into 3 equal parts. 1, 2, 3. And I remove this middle part. Wipe it out. And I raise an equilateral triangle on this middle. Like this. Of the same length. So I remove this and I raise this. Is it okay? I take a straight line, divide into 3 equal parts, remove this part and raise a small equilateral triangle like this. So this is what I get. Okay, so I will go back. Sorry. So this is the first stage, stage 0. Earlier in Sierpinski triangle, the stage 0 was an equilateral triangle. Now it is a straight line. So I divide it into 3 equal parts and I raise an equilateral triangle, same length. This length is same as this length. This length is same as this length, and so on. And then I repeat the same thing on all these 4 smaller line segments. What do I do? Each line segment, I divide into 3 equal parts, remove the middle part and raise a small equilateral triangle. So what do you think the next stage will look like? Well, if it was a physical in-person workshop, I would ask you to draw on your paper or notebook. But this is what it will look like. And then it goes on. So you see, how do I get from here to here? So this is stage 0, this is stage 1, this is stage 2, stage 3. So how? Why? How do we get it? So let's look at this stage. Let me change the color of the pen. So I had divided it into 3 equal parts. I remove this, so this is blank, and I raise an equilateral triangle here. Now to get this stage, I divide this line segment into 3 equal parts. I raise a small equilateral triangle and remove this. In this line segment, I divide into 3 equal parts. I do this. This also I divide into 3 equal parts, remove this like this. And in this line segment, I divide into 3 equal parts, remove this. So what I get is this, 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 this. Right? The black portion which I've drawn is actually stage 2. And in stage 2, I repeat on every small line segment the same thing. Again, it's a recursive construction. Now, do you see? By stage 4, it becomes fairly complex, very intricate and very complex. But again, some simple counting activities can be done. This is called the Koch curve. This fractal is called Koch curve and named after the mathematician Koch. And is a geometrical fractal which can be processed using a recursive process. So, of course, this picture has been generated using a Mathematica code, which already has an inbuilt command for Sierpinski triangle, all the fractals. So it has Koch curve also. So I just said that create the graphics of Koch curve as I goes from 0 to stage 4. So it gives you all the stages, right? Now something interesting happens. If you do this again on an equilateral triangle, so coming back to an equilateral triangle, if I do that process of the Koch curve on each side of the equilateral triangle, so what will I do? I will take this side. I'll divide it into 3 equal parts. I'll remove this part and raise an equilateral triangle of this length, right? Same thing I'll do on this side. I will divide into 3 equal parts, remove this and raise an equilateral triangle of this. And I'll do the same thing for the third side, right? And I'll get stage. So this is stage. So this was stage, the original triangle was stage 0. So from that I get stage 1. Sorry. So this was stage 0. This is stage 1. I repeat the same thing on each of these small line segments. I get this, which is stage 2. And finally, this is stage 3, and it can go on forever. Again, you can ask, what questions would you like to ask your students?
Pertanyaan yang akan dilontarkan ke siswa apa, Bapak Ibu? Silakan, kira-kira apa yang akan diberikan ke siswa pertanyaannya? Anybody? Silakan.
If anyone wants to share, or if you are just curious, what is making you curious? What would you like to explore in this construction process?
The number of angles.
Number of?
Angles.
Oh, okay. Which angles?
Circumference.
Okay. So number of, maybe you are trying to say one could be number of line segments, right? How many lines are there?
Yeah.
The other thing could be perimeter, like you are saying circumference. So I think you mean the total length, right? The total length of the curve, right? That would be very interesting. Yes. Anything else?
Symmetry, they say.
Yes, very, very good. So these are symmetrical. How many lines of symmetry are there in, for example, we know equilateral triangle has 3 lines of symmetry, right? So equilateral triangle, has 1, 2, and 3 lines of symmetry.
Yeah.
But when you have the star-like shape, stage 1, will it have 3 or more lines of symmetry? So it will have line symmetry as well as rotational symmetry. So it's a very excellent thought that you can actually ask children to explore symmetry in different stages of the fractal. In fact, this will have a rotational symmetry of order 6 because it has 6 spikes coming out. So that could be a very interesting thing to explore. But if you just want to do counting activities, what would you like to count? So here are some questions for you. How many line segments are there at each stage? Now, can you just count the line segments? Here there are 3. I don't need to count. At stage 0, there are 3 line segments. How many line segments are here in this stage?
12.
12.
12. But did you count?
Did you count or dihitung atau dengan rumus?
Count.
You counted.
Count one by one?
Yes, that's 12 you said, right?
Yes, absolutely.
1, 2, 3, 4, 5, you can count. Okay, easy to count, no? But now, okay, will you count here and here? How many here and how
Bukan
many
untuk
here?
yang ini.
Mau dihitung satu-satu, Bapak Ibu?
For student uncountable.
36.
11 kali 4 kali 4.
No, but it is countable because
Too
see,
many.
I think someone is trying to explain how did you get 12 here? Because each single line, yes, each single line gave rise to 4 smaller lines. Do you agree with that?
Yes.
Each line gave 4 smaller lines. So 3 times 4 is 12. So this gave 4, 1, 2, 3, 4 smaller lines. This side gave 1, 2, 3, 4 smaller lines. And this side gave 1, 2, 3, 4 smaller lines. So there are 12. Now each of these line segments is split into 4. Let's see how. Let's look at this line. What happens to this in this stage? It becomes 1, 2, 3, 4. So the same thing is happening to any line segment. Here this is 1. It is giving 4. 1, 2, 3, 4. Like that. So how will we count the number of, without counting, can you tell me what will be the number of line segments at this stage? There are 12 line segments.
48.
Yes, very good. How is it 48?
We can use see the ruler.
12 into 4, right? So 4 into
3
4.
multiple 4 multiple 4.
Times.
Yeah.
Oh
You
no.
got the pattern. You got the pattern. So
Yeah.
now, what is it here now? So this was 3. 3 times 4 is 12.
192.
12 times 4 is 48. And now 48 times 4 is how much?
192.
192.
192.
There are 192 tiny small segments. I will not count, but it is so. So now can we find a rule for the nth stage? Again, if this process goes on till infinity.
Yeah.
What noise? I think someone needs to be muted.
Yes.
So if there is this kind of process is continued for a long, then what will be the rule? The number of line segments. The number of line segments at the nth stage is something that we can look at. So it's better to make a table, but I'm just asking you. Then another interesting thing. Suppose this length is 1 unit. What is this length?
Berapa panjangnya Bapak Ibu misalnya? Jadi berapa? Kalau itu 1, segitu 1, 1/4.
1/4.
How much is this?
1
One.
per 4. 1 4.
No. It will be 1/3. Why? Because
Yeah, because
I
Oh, yeah,
divided
yes.
three. There were 3 equal parts.
Yeah.
And I removed the third middle one. So I'm left with 2 parts. So this is 1/3. This is also 1/3.
yes.
And this is also 1/3. And this is also 1/3 and so on. Okay. So this is 1 unit. This is 1/3. How much is one line segment here? Only one, small. Again, this
1 9.
yes, absolutely. So this is 1/9. And this tiny line segment here will be
127.
27.
perfect. Perfect. So basically, the line segments, if you take one line segment of each stage, it's a power of 1/3, right? 1, 1/3, 1/9, 1/27, next will be 1/81, and so on. So we can look at different attributes of this factor. So you can calculate, Wahid was also saying, we can look at the perimeter. Perimeter, because this is a closed curve. So the total length of all the line segments, the total length will give me the perimeter or length of the entire curve. And we can look at perimeter, we can find a formula at the nth stage, and then when you look at area, how much area there is inside, right? So all these things can be done. So I would like you to look at this table where we again, like in the Sierpinski triangle, you can number the stages. This is stage 0, this is stage 1, this is stage 2, this is stage 3. So stage 0, this is number of line segments, S of n, S subscript n, this is 3 line segments. Here it is 3 times 4. This is 3 times 4 into 4. So that is 3 into 4 square, which we know was 48. This is 192. So this is 3 into 4 cube. So if you write it in this form, 3 times 4, 3 times 4 square, 3 times 4 cube, and so on. At the nth stage, there will be 3 times 4 raised to the power n. So once you see the pattern, you can easily write the formula for the nth stage. Maybe this is suitable for slightly older children, maybe grade 10 or 11. And if you look at the line segment, this is 1. Suppose this is 1. This length is 1. This length is 1/3. This length is 1/9. This tiny length is 1/27. So if I write it length of one line segment at every stage, I have 1/3, 1/3 square, 1/3 cube, and nth stage will be 1/3 raised to the power n. But how do I calculate the total perimeter? Perimeter, do you use the term perimeter in your curriculum for total, like for a square, the perimeter is 4 into side length.
Yes, the total or the sum of the sides length.
Lines, yes. So here, the total perimeter will be what? Here, for example, what will be the perimeter at stage 0?
3.
Yes, so 1 plus 1 plus 1. So that is 3. So you will notice one thing. What about the perimeter here? This is 1/3 is one segment, but there are 12 such segments. So it is 12 into 1/3. Because there are 12 segments, each is 1/3, 1/3, 1/3, 1/3, and so on. So 12 line segments into 1/3. That will be the perimeter at stage 1. What about stage 2? Each line segment is 1/9, but how many line segments do I have? this was 48 line segments. So 48 into 1/9 will give me the total length of this curve, right? Should I explain it again?
Yeah, sure.
So we are looking at the total length or the total perimeter. So if this length is 1 unit, this length is also 1 unit, and this length is also 1 unit. Total is 1 plus 1 plus 1, which is 3. So the perimeter, I'm talking about the perimeter. This is 3. Here there are 12 line segments, and each line segment is of length 1/3. So the total perimeter is 12 into 1/3, which is 4. Right?
Yes.
Yes.
Here, yes, there are 48 line segments, and each line segment is of length 1/9, each tiny line segment. So 48 into 1/9. And here there were how many line segments? Small 192.
192.
Yes. And each line segment is of
1/27.
and it goes on like that. But I have to find a formula for the nth stage. So if I write this 12 as 3 into 4 into 1/3, here I write 48 as 3 into 4 square into 9 is 1/3 square. And here I write this 192 as 3 into 4 cube and 1/27 as 1/3 cube. Then I see a pattern of the way of writing this perimeter. So the perimeter at stage 0 is 3 times 1. Perimeter at stage 1 is, so this can be written as 3 into 4/3, 4/3. This can be written as 3 into 4/3 square, because it's 4 square upon 3 square. This can be written as
8 times over 3 to the power of 3.
so. At the nth stage, I can get the perimeter to be written as 3 times 4/3 raised to the power n. So area, length, area, perimeter, all these are ideas that you can play around with in even in this a little more complex fractal, but again a very beautiful fractal because it leads to some very interesting ideas. The most fascinating, and of course we can find recursive rules like we did for the Sierpinski triangle also. But I want to ask you a question. Suppose this is stage 0, this is stage 1, this is stage 2, this is stage 3, and I continue this to infinity. What do you think will happen to the area inside this curve? So there's an area here, some area inside. What's happened to the area now? Has it increased or decreased or?
Areanya semakin luas atau semakin sempit kecil, Bapak Ibu?
Makin luas areanya.
Larger?
Semakin luas.
Has it increased or decreased?
Increase.
Yes. Why has it increased? Because I already had this triangle and I have included 3 smaller triangles, right?
Yes.
I've added 3 smaller triangles. The area has increased. Now from stage 1 to stage 2, has the area increased further?
Increase.
Yes, because to get this stage, at every line segment, I have included a small triangle. Right?
Yeah.
And so on. So as n increases to infinity, what will happen? Do you think what will happen to the area?
Akan menjadi lingkaran ya?
Would be a
Mendekati
circle.
menjadi sebuah.
He said would be a circle, almost a circle.
So what do you think? Will the area also go on increasing? Okay. So quickly, what I will should we take a short break? Wahid, you can tell me if
Okay.
we take a break.
Okay.
I'm
Bapak
okay,
Ibu.
but you ask the
Yeah.
audience, yeah.
Oke, Bapak Ibu, diberi jeda istirahat 15 menit. Jika ada pertanyaan disimpan dan bisa ditanyakan setelah istirahat. Sembari itu bisa ke belakang, bisa minum, dan kita kembali lagi 15 menit. Ya, oke. So I've told them a break for 15 minutes.
15 minutes? Okay, great. So I will complete the chord snowflake on the spreadsheet. I will show after the break, and there are
Yes.
more problems waiting. So let people drink some water and freshen up and come.
Yeah.
Yeah, thank you. So
Okay.
another 15 minutes, you say?
Yeah.
Oh, great. I'll be back.
Okay, thank you very much.
See you again. Yeah.
Jeda istirahat 15 menit ya Bapak Ibu ya.
Should I stop sharing?
Yeah. Sure, you can.
Great. So, yeah, so because I thought that after a break, people can again continue. So they don't have to leave this, they don't have to.
Ya.
Okay.
Ya, tetap berada di Zoom ya Bapak Ibu ya. Kita jeda 15 menit.
This is a snapshot of what students did. So if you give them a dotted sheet, this is called isometric dotted sheet.
Ya. Titik-titik kertas bertitik yang jaraknya sama Bapak Ibu. Nanti bisa saya berikan file.
Yeah, the isometric sheets has dots like this. It's not a rectangular grid, but dots like this, right?
Yeah.
So it's easy to draw a triangle, and so this is the kind of sheet they were given. So this is a student's work, a picture of student's work. So they use dotted paper to draw the snowflake at various stages. Stage 0, then stage 1. So each line segment is now divided into 1, 2, 3, 4 parts. And each of these line segments is now divided into 1, 2, 3, 4. So there are stage 2, stage 3, and this girl, the girl child, student, she did this very small, intricate work with a thin pen. So it was like an artwork. And the drawing became challenging after up to stage 3. It is difficult, but it can be done. Stage 4 is very difficult with a pen, but this child has done. So I took her permission for a picture, and so this is something like this. And and these are some greeting cards which were created by children by folding and cutting. And then when you open it out, these are called pop-up cards. So if you notice that this part looks like the Sierpinski triangle, which has 3 smaller parts. And this is a very interesting activity. Maybe in future, if I get online interaction, I can show you how to make these cards. And I also have a book I can share with you which explains how to make this card. So I can share some resource materials which you can use, which shows you how, for example, if you look at this card, this big cell is 1, but the next size cell, there are 2 cells. And the next there are 1, 2, 3, 4. And the next there are 1, 2, 3, 4, 5, 6, 7, 8. So there are powers of 2. So, there are explorations you can do after making the card. Now, this was the basic card. One student decided to do her own innovation, and she did 2 of these, and she made it a very different card. This is a well-known Sierpinski fractal card. These are called fractal cards. So there is a lot of mathematical exploration which can be done using scissors and paper. So these are cards are made by folding and cutting. And I will share resource material with you using which you can make these cards. But simply using paper, this is one drawing activity. And I think I can show you one more if it's possible. Yes. This is done with a square. It's called the Sierpinski square carpet. Here you have a single square at stage 0, and you divide this into, let's see if I can show you. So you divide it into 9 equal parts. 9 equal square, then you remove the center square. You get this whole. And then each of these squares can be further subdivided, and you get. So this is done. This is a paper model made by a student.
Yeah.
So student asked they challenged other children to find the area of the red portion and so on. So definitely, and in fact, this is another work. One student did this stage 0 and divided into 9 squares and removed the yellow squares. And from the black portion, repeat the same process, and you get powers of 5 in this geometric sequence. And the number of black squares forms 1, then 5, and then 25, and 125, and so on. This is a self-designed fractal of the student. And this is, I have some videos I have created, I can share also with you. The world's largest Sierpinski carpet in Almeria in Spain is a basketball court, which was designed, the floor of the basketball court is designed as a Sierpinski carpet. It's a fractal. So it's a very interesting activities you can do with children. And I will be happy to share some of those things. What was the second question, Vahi?
The second question is, you provided us with the triangles and then the cog. Would there be any other things that students can try with other shapes or?
Oh, yes, yes. A very interesting question. In this particular, so one is the triangle, which we did the Sierpinski triangle. Then I just showed you the Sierpinski carpet. Okay. So I will share the link of a YouTube video which I have created, which has more pictures of fractals. So this is the Sierpinski triangle. Then I showed you the Sierpinski square carpet. This is the Koch curve, which is on a single line segment. And if you repeat this on a triangle, you get the Koch. This is called the Koch snowflake. It's called a snowflake because as you increase this to higher stages, if you ask children what will happen at very large stage, so they say it will form a circle. Many of them say it forms a circle, but it doesn't form a circle. What happens is that these portions tend to get extended, and it looks like a it looks like a snowflake. So that's why it's called the Koch snowflake. So yes, there are many other fractals, but some of them are very complex. So for school children, they might be difficult, but the easier ones are these. And I wanted to share with you that one little experiment which you can do with the spreadsheet. So can I take you to the spreadsheet? Can you see the spreadsheet?
Yeah, we could see.
No?
We could.
We can, okay.
Yes.
Yeah.
So let me take you to, right. Now, again, suppose the same Koch snowflake. So we know that the number of line segments we have seen the perimeter. Now, what happens to the area? Area enclosed by this curve. So suppose I place 0. Now let me have stage numbers, like we did in the Sierpinski triangle. Same way, I have stages from say 0 to 20. And now, what is the formula for the number of line segments at any stage?
1.
Yes, at stage 0. But what was the formula? So here it was 3 into 4 raised to the power n, right?
Yeah.
So we will type here equal to 3 times, for times you can use star, 4 raised to the power, instead of n, I will click on this because the stage number is in column A. So this is interesting because I can actually, so you know that at stage 0, it's a triangle, so there are 3 line segments. But if I do a double click in the corner, I will get the lines. You remember at stage 1, there were 12 line segments.
Yeah.
At stage 2, there were 48. And at stage 3, there were 192, which you had already counted. But stage 4 is hard to see because there will be 768. And very quickly, the number of line segments are growing very fast. Again, it's a geometric sequence. I think I missed out one thing. I should say length. Length of line segment. Let me wrap this up. The text. Then perimeter. Then additional area. We'll look at them separately. Something very interesting happens when you look at the area. Total area inside the. Now see, coming back to the picture here, the number of line segments is 3 raised to the power n. The length of one line segment was following powers of 1 upon 3. So if I put that formula for the length of line segment, I will put equal to 1/3
To the power.
raised to the power n. Again, for n, I will click on A2. So when I press enter, I can go and double click here. So we can see that first stage, the line segment is 1. Then it is 1 upon 3, so 0.33. It's giving decimal representation. Then 1 upon 9 is 0.11 and so on. So the length at each stage of the line segment is decreasing. And here it becomes very small. That's why it is E minus 0.5 means 5.08 into 10 raised to the power minus 5. So if I drag this column, you will see that actually that significant digits has been specified. So this is a very small number. So this, we can see that the length of the line segment is decreasing. So what was the formula for the perimeter? If I don't remember the formula, it's okay. But I know one thing, that perimeter is number of line segments multiplied by the length of each line segment. Is that okay with everybody?
Yes.
The total length of the curve is number of line segments, I tap on that, multiplied by the length of one line segment.
Yes.
What happened to column C? Anyway, oh, okay. I must have hidden it. Okay, doesn't matter. So I have 3, 3. So let's just calculate the perimeter.
Longer.
No, there's some problem here, right? Oh, okay. So let me see if I can unhide what happened to the, oh, right. Okay. So what if I delete this column?
It's okay.
It should make sense. Let me do this again. This is equal to number of line segments multiplied by each segment, and I double click here. Okay.
Yeah.
So let's see what's happening to the perimeter. So if we actually graph them like we did in the case of the Sapinski triangle, I can click go to charts, select a line graph option. So we see the line segments are growing exponentially. I can reduce the size and place it here. Let's see what's happening to the length of one line segment for each stage. Just the reverse is happening. The length is becoming very small. It is going down. Let's see what's happening to the perimeter. Perimeter is increasing again. Two things are increasing. But the problem is, we can see here that the perimeter is increasing, the number of line segments is increasing. But can we compare these two actually? Which is increasing faster, the number of line segments or the perimeter?
Perimeter.
Perimeter is increasing faster than the
Yeah,
number of line
faster.
segments.
Faster increasing.
Now let me delete this one.
Line segment, perimeter.
Which one is increasing faster? Both are increasing. This is increasing, this, which is increasing faster?
Line segment.
How do we check? How will children check? See, the scale is very different, right?
Yes.
Yes.
Here it is very big scale. It is 4 into 10 raised to the power 12, and it's only 1000 here.
Yeah.
So how to compare? I can't compare these two, you know. So what I can do, that's why this call, I was trying it out yesterday. So what I can do is, I can select, no, I can select, let me hide this column. I hide column C, and I just look at line segments and perimeter. I select, so if I can select column B, press shift and select column D, select both the columns. And let's draw a graph with both of them. Now I'll delete this because there's no space. Now look what's happening here. The number of line segments is the blue graph and the perimeter is the green graph, which is stuck here. But I can't see what is happening really. So what I can do is I can change the scale. See, on the x-axis, what are these numbers? What do they indicate? The number on the x-axis?
This is what you need.
Is the
Increment.
is the stage numbers.
Yeah.
The stage numbers are on the x-axis. On the y-axis, I have the values of these. So what I do is, let me see if I can change. I can go to format axis, and I can change the maximum value to, let's say, 2000. Now what's happening is that the number of line segments is the blue line, blue graph, and the perimeter is the green graph. But they are comparable because they are, I mean, you can see them both clearly. Now, can you say which is growing faster?
Line segment.
Line segment, absolutely. This is just shooting up very fast, and this is growing, but growing slowly. So the growth can also be you can talk about the growth, which is growing faster, which is growing slower. So graphical representations are important if you have to, explore. So this is an interesting thing, which I thought I should point out. Then I can unhide, I can select the columns, right click and unhide and bring back column C. Now my question to you was, I'll delete this. that what happens to the area enclosed by the chord snowflake as we go on increasing the stages? What happens to the area inside the curve? Is it increasing? Is it decreasing? What's happening? So we saw that it is increasing initially because from the triangle it becomes this, and from this it becomes this, and so on. So it seems to be increasing, right? But how do I, okay, so let me ask you. Yeah. These are the graphs, yeah. So I will come back here, yes. So what is happening is that, do you know the formula for the area of an equilateral triangle?
The area of equilateral triangle?
Yes, do you teach the formula to children or?
Yes.
Yes.
So what is the formula? So suppose this length is 1 unit. What will be the area? Do you use this formula, √3/4 into side square?
The circumference minus the S minus A minus.
Oh, okay. Heron's formula. But in this case of an equilateral triangle, we get this formula, which is √3/, I mean, you can do half base into height also, no problem. But for that, I have to calculate the height. So
Yeah.
there is a formula, direct formula, which says the area of an equilateral triangle is √3/4 into the side square. So if the side is of length 1, then what will be the area? It will be just √3/4 into
And
1 square, which is √3/4. Right? So the area at stage 0, this is stage 0 of the chord snowflake, is √3/4. Now what will happen to the area here? So if I do stage 0, this triangle is stage 0. It already has area √3/4, but I'm adding 3 smaller triangles. What is the area of each of, what is the length of this?
Square root of 3/4 times 1/3 square.
Yes, each of these triangles. So the first triangle is, did someone raise a hand?
Yes, Budi Santosa, I think.
Yes.
Mr. Budi, do you want to say something? No, I think mistakenly.
Okay. So √3/4 is the initial area. Now 3 small triangles get added. These are all equilateral triangles. So 3 equilateral triangles multiplied by the area of this triangle. Let's take one triangle. What will be the area? It will be also an equilateral triangle. So √3/4 into the square of the side, which is 1/3. So 1/3 square. But there are 3 triangles. So I've put it like this, right?
Yes.
Now, let's come to the next stage. How many new triangles have got added to this stage? So there is a tiny triangle here. I'm going to shade those triangles. 1, 2, 3, 4. There are 12 of them. 5,
Yes.
6, 7.
12.
Okay.
Yes. 8, 9, 10, 9,
10, 11.
12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each of these triangles has area √3/4 into multiplied by the 1/9 square. Excellent. But there are 12 such triangles. So total area will be 12, which is 3 into 4 times the area is one triangle is √3/4 into 9 square. Now I'm trying to write this in terms of 3 and 4 only.
Mhm.
So 1 upon 9 square can be written as 1 upon
3
3
to the power
raised to the
4.
power 4. So there are 12 triangles, each triangle having this area. 12 has been written as 3 into 4. Now, one more term, if you can help me write just one more term, it will be a very interesting thing. So it will be difficult to shade those small triangles, but there are how many line segments? See, here there are 3 line segments. Here there are 12. Here there were 12 into 4, 48 small line segments. Each of those 48 line segments have a tiny triangle sitting on it. So the additional number of triangles at this stage is hard for me to color, but I can write. There is abstraction. Mathematics allows us to do that. It is 48, which is 3 into 4 into 4. So 3 into 4 square, 48 into. Can you tell me the area of each of the triangles that will be a small tiny triangle, which is an equilateral triangle, which will be root 3 upon 4 into
1/3. Yes.
1 by 27 square.
Yeah.
Right? Here, this triangle had area root 3 upon 4 into 1 by 3 square. Here, the small triangle had area root 3 upon 4 into 1 by 9 square. The next will have root 3 upon 4 into 1 by 27 square.
Yeah.
Yeah, 27.
Do you agree? A very small triangle here will be root 3 upon 4 into 1 upon 27 square.
Yes.
And if I have to write 27 square as a power of 3, what should I write?
8.
Pardon?
8.
Eight.
6. 6.
Six.
6.
6.
Yes, absolutely. And I'm not going to go any further. But suppose this goes to infinity, right? Now let's try to play around with this expression. I mean, we are all mathematicians after all, right? Let's play around. I want to see, as this process goes to infinity, what will be the area enclosed by the core snowflake, right? So I'm going to play around with this thing. Let's keep root 3 by 4 aside. And now let's look at this term, let's look at this term, let's look at this term. And we can predict the next few terms because we have seen the pattern. And this can be an excellent task to do with grade 11 students or even 12 because they study arithmetic and geometric sequences and all. Is there something common in these terms which I can keep outside the bracket? And so 3 into root 3 upon 4 into 1 by 3 square is here also. And is here also, right?
Yeah, the 3.
If I say 3 into root 3 upon 4
And
into 1 upon 3 square.
3.
And
1 of the 3.
so this is common. So this is 1.
Yeah.
Plus here I have already outside 3 root 3 upon 4 and 3 square. So it will be 4 upon
4 multiply
3 to the power 2.
3. 2.
Yeah.
Is that correct?
Yes.
Yes, got it.
Wonderful. Now
Plus
next, can you tell me what will
plus
come from here?
4 square.
Okay. So I already have 3 and root 3 upon 4 and 1 by 3 square outside. So I can say 4 square.
4 square. 4.
3
3.
to the power of 4.
3 over 3.
3 raised to the 6 here and
3.
3 square outside. So 3 raised to the power 4.
4.
and I don't have the next term here, but if it was there, what would I write here? What is your guess?
Power of 3.
4 raised to the 3, okay,
To the 3
To the power of
upon
3
to the power of 6.
or 6.
because the powers of 6 are powers of 3 are even, and powers of 4 are 1, 2, 3. So this goes on and on. But why did I do this? How will it help me? What is this? This is a geometric series.
Yeah.
And do you do this formula that in a geometric series, the sum to infinity, if the
Yes,
common
we do.
ratio, the multiplying factor, if it is less than 1, then I can use the formula S infinity is equal to A upon 1 minus R.
Minus R. Yeah.
R is the ratio. And
Yes.
only this can be used only when the absolute value of R is less than 1.
Yeah.
So here, what is the R here? What is A here? A is equal to
1.
1. And what is the ratio here?
4.
4 upon
4 over 3
3
to the power of 2.
3
2.
squared, which is 4
Yeah.
upon 9, right?
3
3
square.
square. Yeah.
Wonderful. Now, can you calculate what A upon 1 minus R will be? So this bracket expression is equal to 1 upon A is
1 over 1 minus
4 upon 9.
yeah 9 over 5.
9.
9
9 over
4 F.
Yeah, exactly.
9
So
over 5.
9 over 5. Yes. So if I have 3 upon 4, root 3 upon 4 plus, now I can cancel this 3 here. So I have root 3 upon 4. Sorry, my pen is, you can do the calculation, root 3 upon 4 into 1 by 3. And the bracket is 9 upon 5. So what do I get? Can you do this calculation? Root 3 upon 4 plus root 3 upon 4 into 3 by 5. So I have root 3 upon 4 common. I have 1 plus 3 upon 5. After cancelling the common terms, what does this lead to? Is it
8
okay?
over 8 over 5.
8 over 5, yes. Which
And
again,
then 2 over 5. Yes.
2 upon 5 into root 3. So root 3 is about approximately 1.732 and 2 upon 5 is 0.4. So as the Scotch snowflake grows infinitely, the perimeter grows infinitely.
No.
But the area seems to approach a fixed value, which
Yeah.
is root 2 upon 5 root 3.
Mm.
Now, it's very fascinating because when you do this work, the children get excited, but then they say, I mean, this is theoretical, and this we've analyzed it mathematically, but can we see the numbers? Is it actually happening? So let's go back to the spreadsheet. I hope you're okay with this calculation and how we did it.
Still understandable.
Yeah, you can try it yourself. And again, I will share the material with you. But now just see something very interesting. So here, first what I will do is I will calculate the additional triangle areas that are getting added at every stage. Now at stage 0, there is no additional triangle because that's the initial triangle. At stage 1, there are 3 smaller triangles. So what will be the total area? It will be 3 times, oh, I'm sorry. I need to
3 over 4.
root 3 upon 4. So let me calculate root 3 upon 4 in a separate cell. SQRT, square root 3 upon 4. So the command is SQRT 3 upon 4. That value is 0.433. So this we need. We need root 3 upon 4 in our calculation. Now, the additional areas at stage 1 were, there were 3 triangles on each line segment. So 3 multiplied by root 3 upon 4, which is this value in H1, cell H1. So to fix the value, I will use dollar symbol, $H, $1. Otherwise, this value will change. So whenever I put $H, $1, it means it is the value of root 3 upon 4, which is 0.433. So what was there? How many additional triangles were there at stage 1? There were 3 small triangles. So a total area was 3 times root 3 upon 4 into 1 by 3 square. And 1 by 3 is this value, 1 by 3 raised to the power 2. So using the data from the previous columns carefully, you can actually calculate the additional area at stage 1. Again, I'm repeating, B2 is 3 triangles. This $H, $1 is the value of root 3 upon 4, which I have saved here in the separate cell. And this is the area, 1 by 3 square. Now, because we are lucky, we have a spreadsheet, all I need to do is double click and automatically the additional areas at every stage will get calculated. So mind you that these values are the additional areas which are getting added. So at stage 2, the total additional area is only this much. At stage 3, the total additional areas are only this much. So the first thing that students notice is, oh, the additional area is getting smaller and smaller. So what happens to the total area? Now the total area at stage 0 is of course root 3 upon 4, because we saw that there's a single triangle, area is root 3 upon 4. But here, the total area at stage 1 will be the total area at stage 0 plus the additional area of stage 1. So all I have to do is click on this value, which is the original area plus the new area added, additional area. And when I do that, I get a value 0.577. So from 0.43, which was the initial area at stage 0, the area has increased to 0.57. But if I double click now, oh God. So now, do you see what is happening? So at stage 3, it increases to 0.64. At stage 2, it increases to 0.64. At stage 3, it is 0.67. 0.68, 68, 69, 69, 69, 69, 69, 69, 69, and it steadies out. Now, what was, when we calculated using geometric sequences, our value was 2 upon 5 root 3. Let's calculate. Root 3 is this value? No, this is not the value of root 3, sorry. Square root 3 is, let's calculate. Square root 3 is how much? 1.732. And if I multiply this with 0.4, which is 2 upon 5.
Yeah, 2 upon 5.
So it's 0.62692, which is what is happening.
Yeah.
So it's very interesting because we graphed the perimeter. Now let's graph the additional area. You will see that additional area is going to 0. At every stage, some area is getting added, but that value is getting lesser and lesser, which is why when we graph the total area, then we see very interestingly that the total area increases initially, but then slowly it steadies out. And what is that steady value? If you take the cursor on the graph, it tells you, Excel tells you that the total area is 0.6927 and so on. So there is a huge range of possibilities that you can explore by calculation, by exploring numerically, because you see, theoretical analysis is very good, but it is abstract for children. So what we did on that sheet just now, those calculations was very important, though those must be done. And after doing this exercise, my students of grade 11, they said that, oh, we love geometric sequences and series, and connecting it with these pictures and these diagrams and this construction of the fractal snowflake. It was a very enriching experience for children and for me as a teacher. So I wrote an article on it, and I would like to share that as well. It was published in Mathematics Teacher a couple of years ago. So I explained how children engage with algebraic thinking through the use of spreadsheet and through the Koch snowflake construction. So I hope you enjoyed this. You see, mathematics has the beauty that it's an ocean, and you can go further. Like if you look at only the Koch curve is on a single, same thing, same idea, but on a single line segment. Older students of grade 12, I had given them this project on what we call is matrix transformations. That means those who teach matrices. Do you teach matrices in class 12, in grade 11, 12?
Matrices, yeah.
Yes.
In high school, we have it.
You have in high school? Oh, great. So one of the applications of matrices is transforming the shapes and sizes of figures, right? So for example, just one small example, if I look at the Koch curve, now when I go, this is stage 0 and this is stage 1. What do I need to do? I need to shrink this line. Suppose this is 0, 0. Coordinates are 0, 0. And suppose this has 1, 0. Imagine that this line segment is on the x-axis from the origin to 1, 0. I need to shrink it because if I have to bring it here, I have to make it, this length is 1/3, right?
Yeah.
So I have to make it 0, 0. This coordinate will be 1/3, 0. This coordinate is 2/3, 0. And the point here is 1, 0, right? This distance is not changing. That is fixed. But this has been added. Now, how do I shrink? What will make me shrink this line to this position? 1/3 its size. So, if I use what we call as a transformation, that means if I take, sorry?
Multiply by a constant?
Multiply by a matrix. So what I want to do is I want to map, let's say this is 0, 0, 2/1 matrix. I want to map it to 0, 0. Because 0, 0 has to go to 0, 0. And 1, 0, which is this point, has to go to
1/3 0.
Yes. I hope it is clear to everyone. So I can use the transformation F1. Suppose I have an ordered pair XY. I multiply it by this 2/2 matrix. 1/3, 0, 0, 1/3. XY. Now, instead of XY, if I put 0, 0, what will the multiplication give me? If I multiply this with this and putting X as 0, Y as 0, I will get 0, 0. right? If I put 0, 0 here. So this into this, row by column, 1 by 3 into 0 plus 0 into 0 is 0. 0 into 0 plus 1 by 0. I'll get 0.
Yeah, 0.
But if I place 1, 0, if I take this matrix 1 by 3, 0, 0, 1 by 3, and multiply it with 1, 0, I get 1 by 3 into 1. Yeah. And this will give me 0.
0.
So this is the matrix which shrinks this line segment to this line segment. Now I need another matrix which not only shrinks this line segment to this line segment, that is 1/3 its size, but also rotates it by 60 degrees.
60 degrees, yes.
So I need a shrinking and a rotation. So what I do is, my shrinking matrix is 1 by 3, 0, 0, 1 by 3. Sorry. And my rotation matrix is cos theta. Cos, in my case, theta is 60 degrees, minus sine theta, minus sine 60 degrees, sine theta, sine 60 degrees, and cos 60 degrees. Pardon me, my pen is acting strange. But so when I multiply these two with x, y, whatever the coordinates are, x, y, it will rotate, it will shrink that lines that point to this 1/3 its size and will also rotate it by 60 degrees. So I have another transformation which will transform this to this line segment. Then I need a third transformation which will transform these to this line segment. And finally, I need one transformation so I need a set of 4 transformations which will convert stage 0 to stage 1 of the Koch curve. These are called iterated function systems. So let me sort of just quickly show you what it is. I'm not going to do the calculation, but these are the transformations. So this is the transformation which shrinks the line. So this original line, this F1 will shrink it to 1/3 its size. F2 is the product of those two matrices which I just showed you, but it has to be shifted. This line has to be shrunk, rotated, and shifted to this position. That shifting is done by adding this matrix. So F2 will lead to this line segment, F3 will lead to this line segment, and F4 will lead to this line segment. A sequence of 4 matrix transformations will convert stage 0 to stage 1, and repeatedly from stage 1 to stage 2. So if you are planning to teach application of matrices to older students, then again, this is a great exercise to try. So we are at nearly at 6 o'clock.
Yes.
I think everyone must be tired, but if I have 15-20 minutes more, I can show you a new problem and maybe you can try it out. Would people like that, or would you like to ask questions? And it's up to you. So
maybe it would be wise that it would be a questions and then the task will be a homework for them.
Okay, great.
Okay. You can send the file to me and I will upload it to the Google Classroom so they can work on it.
Okay.
Okay, so actually there is a questions before that you haven't answered it. That when you work with spreadsheets and it showed up or show the E for the exponents, right? The E symbol on the cell when you calculate. So for students, how would you make it understandable for students for that case when E appears?
Correct. Interesting question. And that does come up. Okay, so let me write it down. So what I explained is that because Excel has a rounding off system.
Yeah.
Suppose I have 5.0879 E say -5 like this,
Yeah.
or I have 4.0321E4. Now, Excel rounds off to certain significant figures. So if I had rounded off the given number to say 1, 2, 3, 4, 5, 5 significant figures, it may give me this. But the meaning of this is 5.0879. The E minus 5 is actually
Hence,
into 10 raised to the power -5. So this E is not the 2.718, not the Euler's E. But this
Yeah.
capital E is the exponential 10 raised to the power -5, which means it is 5.0879 divided by 10 raised to the power 5, which is
100,000.
Yeah. Yes. And therefore, the decimal will shift to, so it will become 50879. So 1, 2, 3, 4, 5, and then the point. So it's a very small number, 0.00005. But on the other hand, if it was this, it would be 4.0321 into E is 10 raised to the power 4.
4.
It's a big number. I mean, you will multiply this by 4. So 1, 2, 3, 4. So approximately, these are all approximate calculations. So 40321 and so on. So this has to be explained on the board by see, because this is just a notation. It's a scientific notation that Excel uses. So you are very right that when we see like here. So suddenly this is 0.000, a very small number. And then, oh, but this is a big number. No, it's not. Then you have to explain to them why this is, what this means. Maybe there's one more zero here after the decimal point, and this is a smaller number than this. So this, yes, this part has to be explained, yes.
So, Dr. Junaki,
Yes.
you explain it before they explore the Excel, or you explore it when they
No, when
find
it comes up, yeah, when they find
When
it.
it's-
Because technology will bring up surprises, and it is important to be prepared for those surprises and explain them when they come.
Balik, Mama. Tala balik bolongan itu. Itu balik.
Okay. Okay, any other questions? Ada pertanyaan lain, Bapak Ibu? No? So, maybe I would like you to clarify this. So when they play with the Microsoft Excels, they also have the hands-on activity also, right?
Yes, yes, yes. It's all
And then,
together. Yeah, yeah.
yeah, combine all those two.
Yes, yes. Actually, I will explain. It is best to give it as a, you divide your students into groups. Say, what are your class sizes, like roughly how many students in the class? About
Berapa banyak siswa Bapak Ibu biasanya? 24 sampai 28? 22? 32?
36.
Itu. 36.
30.
30.
30.
Okay. So even if you have 50 students, it doesn't matter. You can divide them in groups of 4 or 5 and let everybody do the basic fractal exploration. Let's say Sierpinski triangle is simple to understand. So don't start with Koch snowflake. Do Sierpinski triangle, or you start with the Sierpinski carpet. Okay, I will share the video with you. Then ask them to create their own fractal explorations and their own designs, and observe self-similarity. Like in higher copies, can you see smaller copies and so on? Okay. After that, you can also ask. So then you say that each group can extend this to in whichever way they feel like. So one group may like to do the drawing. Maybe I'll stop. So one group may like to do drawing like this group. Sorry. The one I showed you on called Snowflake. The girl student, very good in artwork. So she preferred to do the extension this way. But some other students said, so one group did this work. Somebody else might try to do this kind of an idea on some other shape. So one group, a student asked me that, can't I do this on a square? This idea of trisecting. So if I take a square like this, can't I? I said, please try. So they said, okay, what we will do is we'll divide the side into 3 equal parts. We'll remove this and we will install squares on all the 4 sides. And we'll keep repeating this process here every time. Will it become a fractal? So I said, well, can you find self-similarity? So this was a completely new thing, because this idea was a new thing. They were trying to apply the idea of the Koch curve onto a square rather than a triangle. So it is difficult to predict what students will think like, but it is important to encourage them to think innovatively in new ways. So let all the students, all the groups do some part, the same exploration, but when they have to extend exploration, let them try different things. So some group may explore a new fractal, some may look more at spreadsheet exploration, some may focus on artwork. Artwork using fractal can be an excellent resource to do for the school also, where you are teaching. A decorative part, like these fractal cards, which I showed you, they made these big images, very big fractal cards. And these were stuck on, the corners of rooms there was a mathematics lab. And if I get opportunity to do one more workshop with you, I will show those things, pictures of those things. So they're very beautiful things that can be created. So it is important to mix the use of technology with hands-on work also. So some children may be better at hands-on work, some children may be better at the use of technology. It's okay, because everybody is different. Every child is special, right?
Yes, sure. And then there are 2 more questions. Is that okay?
Yes, I'm good. Should I stop sharing right now?
Yeah, sure. So the next question is in the component of computational thinking, the decompositions, abstractions, pattern recognitions,
Yes.
and programs, algorithm designs. Which part of those components are or can be found in your activity here in the Sesi activity?
Thank you for asking such relevant questions. So this was the slide I wanted to show, but I didn't get the time. So how does a fractal exploration lead to CT-MT integration? Now see, this is my thought on this. If I look at the counting process, what are the mathematical aspects and what are the computational aspects, computational thinking aspects? So when you're counting the number of triangles or the number of line segments or looking for patterns, these can be done by grade 7 and 8 easily. This would be more mathematical, right? But creating the same thing numerically on a spreadsheet, what formula will you put in a cell to get the pattern of the number of triangles? What command will you give to the Excel? That needs a thinking which is slightly different from mathematical thinking. And that I would say comes under computational thinking. That is with the process of counting, because most of the fractal explorations will require some counting process, whether it's counting line segments or anything, area or whatever it is. Then there is an idea of recursion. Finding a recursive formula or rules or expressing, for each attribute, we looked at the nth term of the sequence. there was a geometric sequence and we found the nth term. So formula writing and recursive formula that usually done in grades 9 to 12, that is more a mathematical thinking. But when you look at the picture, like we did in the Sierpinski triangle, we looked at the small portion and how many copies are there. So identifying copies of stage n-1 and stage n, or building, I have a very nice, I don't know if you've used this software called Mathicon. It's all open source. Mathicon, you just have these little triangles, you keep building them. So you first create stage 0, then you bring in 3 copies and you make stage 1. Then you make 3 copies and make stage 2. So quite a good stage of Sierpinski triangle can be built. So building higher stages from copies of smaller stages. So this idea of building the fractal is a computational thing. It has, of course, mathematical aspects in it, but it is also computational. Then when we come to generalization, which is a very important mathematical process, exploring the geometric sequences from various attributes. Line segments led to a geometric sequence. Number of triangles led to a geometric sequence. Shaded area led to a geometric sequence. So all these geometric sequences, exploring them requires mathematical thinking, using which matrix should I multiply with so as to get the right shape and size is a mathematical thinking. But simulating those ideas on a spreadsheet or using GeoGebra also, if you use GeoGebra, that would require computational thinking. But what I feel is common to both aspects is exploring these fractal or whichever problem it is, numerically, graphically, symbolically. All of this is a common part of both mathematical and computational thinking.
Okay.
That is my answer, but it may not be the perfect answer. But
yes, I think you have answers the city aspects in the exploration of the fractals. And one more question is that the way to organize these lessons to school or to the students so that the computational thinking is measurable. So of course you will do a kind of assessment in the end, right? Do you assess it or not?
Very good question. Well, actually, I teach in a pre-service teacher education program. So in the first year, the students who pass out of class 12 and join the college, come to college, many of them don't have a high level knowledge of mathematics, but they are studying to be a teacher. So they have to do a foundational course in mathematics, in which mathematical and computational thinking is a part of it. And I do a lot of fractal based activities every year with them. So I do assess them because one aspect is by solving problems, the other is I give them projects and they have to present their project to me as a group, explaining the mathematics, explaining the computational aspects, and then that is an evaluation that needs to be done. But when I do this with school students, teachers have told me that these should be integrated into the topics of the mathematics curriculum. Some teachers have given that feedback. So when for example, if you're teaching geometric sequences sequences and series is a topic in class, let's say class 10 or class 11, then some part of fractal activities can be included as a problem in the exercise of problems. You can include this also. And in fact, our Indian textbook has a very small part which has been included now recently. They were not there before, but very small part. Like in grade 8, they use the chord snowflake just for accounting, but not more than that. So I think it is really up to the teacher. Of course, there are limitations of the curriculum and the time that you must be having a limited time to complete the syllabus that you need to teach. But bringing in these small things off and on, not every day, it won't be possible every day, but inquiry-based learning through these activities will go a long way in building the interest because many children get demotivated with mathematics. They are afraid of mathematics because they think it's only numbers and abstraction, all that. But the moment they get to do things with their hands and they explore the same idea on another software tool, it gives them this generation of children, it gives them excitement. And I think we should provide that excitement to them. So as a teacher, you can design some tasks which you can evaluate them on, or you can prepare a portfolio. For example, I like to do that. So if I have students working on a project for 3 or 4 months, I maintain a portfolio of that group of students. What exactly is each student doing in that project? How are they contributing to that project? What is the mathematical aspect of their thinking and what is the computational aspect? So I do that with my first year college students.
Yeah. Okay. Thank you, Dr. Janaki. I think we are running out of the time right now, but we really love to have you to share your knowledge with us and experience. But due to the time limitations, we have to stop till now. And it was really wonderful. They really want to read your publications or research. If it is available, you can share the link where we can find it, because one of the participants also asked for reading your research as well.
Sure.
So yes, sure. So we're really happy to have you. Thank you very much for your sharing today. I hope it give impacts to mathematics educations in Indonesia. Thank you so much for today's sessions. We really enjoy it.
Thank you.
Yeah.
Thank you very much. One thing I would like to share is before I close is that I will share material with you. If there are more opportunities to do this interaction, it would be very nice. So you'll be the contact point, right? I will share the slides of my presentation, and I will also share my research material, some readings which teachers can read. So I will share that with you. Please share with the teachers. And thank you for being such a wonderful participative audience. And thanks to you, Wahid, for making this possible. Thank you.
Yes.
Okay.
Yes, yeah, it is Saturday night in Indonesia, and they still enjoy your sessions. Like they sacrifice the Saturday night to follow your station, actually. Yeah.
Thank you very much. Thank you. I look forward to meeting you again if possible. Yeah.
Yes, for sure. We are looking forward to having you again. Before we close the sessions, we have 2 door prize that we will give a kind of giveaway to the participants. Would you like to ask one questions, Dr. Janaki?
Would I like to ask questions?
Yes, that they will answer and they will get the door prize from our committee.
Oh, okay. So I have to ask a question.
Yeah, one question. If it is okay, if you not okay, then
Ambil, Kak.
Ambil. Do you want to ask anything?
No, so my question is,
yeah.
My question to you, to all of you, is that how creatively would you like to include fractals in your teaching?
Yeah.
Would you like to include fractals in your teaching?
Nanti kumpulin buat ke tukang rongsok.
I think someone is asking something.
Okay, so it was not clear. Somebody is speaking.
So my question was, would you like to, after having gone through this session, are you motivated to include fractals in your teaching?
Oke, silahkan dijawab Bapak Ibu, ketikan ya atau tidak, Bapak Ibu akan mencobanya. Oh, the first one is okay. The first one. Okay, we'll get the door prize.
Yes.
Okay. Okay, thank you, Dr. Junaki.
Okay, thanks a lot.
So most of them, many of them would like to try these fractals.
Great.
Okay,
So I will
thank
share
you.
more material with you. Yeah.
Yes, okay. Another door prize and another questions. Be ready. Siap Bapak Ibu? Siap untuk menuliskan jawabannya?
Yes.
Siap. Siap-siap ya. Yang paling cepat yang tertulis di chat akan mendapatkan door prize-nya. Komen apa yang diperlukan untuk mengunci sel? Silakan. Komen apa yang digunakan untuk mengunci sel? Oke, dollars. Oke, thank you. Okay, and the winner, the first one is yang pertama adalah Bu Firawati, ya. Jadi yang akan mendapatkan door prize adalah Bu Firawati dan Bapak siapa nih? Pak
Abdul
Girma
Fahmi.
Andalan. Pak Bu Isnaini ya, Ahmad Isnaini ya. Yes, selamat bagi kedua yang mendapatkan door prize tersebut, nanti akan dihubungi panitia. Oke, Dr. Jonaki, thank you very much once again. I look forward to having you in other occasions. Thank you so
very
much.
much.
You
Okay,
may leave
bye-bye.
if you have other agenda. Bye-bye.
Bye-bye. Take care and
Yeah.
enjoy the weekend. Yeah.
Ya, enjoy the weekend also. Terima kasih Bapak Ibu semuanya yang sudah hadir di sesi ketiga ini untuk webinar seriesnya. Mudah-mudahan bermanfaat. Nanti untuk materinya akan saya share di Google Classroom. Jadi dipantau di Google Classroom. Jangan lupa yang belum presensi segera presensi. Ya, kemudian nanti ada tugas yang belum diselesaikan karena tadi sebenarnya masih ada aktivitas dari Dr. Jonaki. Oke, ditunggu di Google Classroom, Bapak Ibu. Saya juga mohon maaf jika ada salah kata atau salah ucap di sesi hari ini. Mudah-mudahan Bapak Ibu memaafkan saya dan presensi ada Bapak Ibu, di copy lagi di atas ya, bentar ya, saya akan kopikan lagi presensinya ya. Presensinya ada di sini. Sebelum leave silahkan presensi dulu, nanti linknya akan hilang ya. Silahkan ya, silahkan Bapak Ibu. Terima kasih, selamat menikmati waktu weekendnya, malam minggunya. Sekarang di Indonesia mungkin masih jam 7:30 lebih untuk waktu Indonesia Barat. Di Indonesia Timur mungkin udah 8:30. Ya, link GC-nya ada di grup WhatsApp ya Bapak Ibu yang sudah digabung di webinar 1-2. Sebentar saya share link GC sekalian ya. Oke. Silahkan diisi presensinya ya Bapak Ibu ya. Ini link GC bagi Bapak Ibu yang mungkin belum bergabung. Happy weekend semuanya. Selamat malam. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.